We're ready to go into the length and area discussion of the Geometry Power Hour. So our three main topics here will be the differences between perimeter and area, the rectilinear area formulae, and compound areas. Starting out with the differences between perimeter and area. These two words both have to do with measuring shapes, and so students mix them up quite a lot. I want to delineate three ways in which perimeter and area are different. Their location, the operation that's used, and their dimensionality are all different. Where is a perimeter located? A perimeter is located on the outside of a shape. The area is located on its inside. If you're going to calculate a perimeter, which operation do you use? You add. To calculate an area, you multiply. And how many dimensions are there in a perimeter? Only one. A one-dimensional measurement is also called a linear measurement. That basically means that you could measure a perimeter with a piece of string as long as you're able to kind of fold or bend the string around the shape. An area is two-dimensional. You can't measure an area with a piece of string. You have to cover it with tiles or cover it with paint or something like that. And two-dimensional measurements are also called planar because they're part of a plane. Okay, so those are three really important differences. There really isn't a formula for a perimeter. It's just a definition. The perimeter means what you get when you add together all of the one-dimensional lengths along the outside of the shape. Add together all the sides of the shape. They have to be straight. It doesn't work for curved shapes. Okay, now area does have certain formulas for it. And that's where we're going to go next with the rectilinear area formulae. Rectilinear, by the way, again means that there will be no circles involved, no curves. Everything is going to be straight and right angles. Well, I guess not necessarily right angles, but there won't be any curves. And of course, formula is the plural of formula. Okay, so the two most important rectilinear formula are the area of a rectangle or parallelogram and of a triangle. And you can see that they're almost exactly the same. The area of a rectangle or parallelogram, area equals base times height. The area of a triangle is half of that, because every triangle is half of a parallelogram. You probably didn't study parallelograms very much when you were growing up, but I consider them to be an important part of this discussion because they lead into triangles. As it says here, a triangle is half of a parallelogram. So there is a certain relationship between a rectangle and parallelogram and another relationship between parallelogram and triangle. So they kind of all go hand in hand. That's why I like to discuss them all together. Okay, now, so this is a very simple formula. Area equals base times height. But the challenge is figuring out exactly what the base and height are. So we need sort of legal definitions for base and height. And on your worksheet, I've written the blank must be a side of the shape. And we're going to fill in that blank with base. So the base cannot contain any of these imaginary, like, dashed guidelines. It has to be an actual solid side of the shape that's being measured. Sometimes I say that the base must be any side, the whole side, and nothing but the side. All right, so what about the height? The height must be blank to the base, and we're going to fill in that blank with perpendicular. The height must be perpendicular to the base. It cannot be a slant height in order to calculate area. So to demonstrate that, let's look at parallelogram KLMN, which is labeled below. So I've labeled this side as 20, this side is 12, and here's an imaginary guideline that goes right down the middle, perpendicular to the bottom, and its measurement is 8. By the way, the word perpendicular has synonyms such as right angle or 90 degrees or square symbol. So the right angle is key to identifying the base and the height. Question number 4 actually asks about the perimeter. What is the perimeter of parallelogram KLMN? Is the answer 32? Is it 12 plus 20? Is it 12 plus 20 plus 8? No, it's none of those. Again, the perimeter just means add together all the sides. So remember that if this side over here is a 12, then so is the other side. And if the top is 20, then the bottom is also 20. Parallelograms have equal opposite sides. So then we can see that the full perimeter is 12 plus 20 plus 12 plus 20. We would not count the 8 because it is not an actual side of the shape. So when we add 12 plus 20, we get 32, and then we double that and we get 64. What are the base and height of the parallelogram? The base must be an actual side of the shape. It can be any side, the whole side, and nothing but the side. So therefore, it certainly can't be 8. The base could be 20 or 12, or again, 20 or 12. But in order to figure out which one of those is more useful, we need a height that's perpendicular to it. So we can see that 8 would be the height as long as 20 is the base. Question 6, does the base of a shape have to be the flat part on the floor? The answer is no. And I emphasize that because it's a very common misconception. Many people think that base means literally like the base of something solid that you would put on the table, the flat part on the floor. It doesn't have to be. It could be. The way this diagram is drawn, 20, you could think about the 20 as being this base Kn down here, or the base could be Lm. It could be on the top of the shape. Sometimes the base might be somewhere else. Question 7, does it matter where the height is drawn? So I drew the 8 here. Does it really matter where it is, or could I put it over here? Oh, man. Is that still the height? Yes, it is. So the answer to this first question, does it matter where the height is drawn? No. It doesn't matter exactly where it's located, as long as it's measuring the height of the shape. But you could take this height and you can slide it even all the way over here. Redraw the height so that it touches point M, which is what I did here. Very important question now. Is it still the height? What do you think? Does this still represent the height of the parallelogram, even though it's outside the parallelogram now? Many students really get fooled by that. They think, oh no, that couldn't possibly be the height of the parallelogram. It's outside now. Well, that's just wrong. It is still the height of the parallelogram. Think about the height as a tape measure. If you're holding up a tape measure to this thing, it doesn't really matter where you hold the tape measure. It's still the height, as long as it's measuring the the perpendicular distance between these two sides. So we still have to make sure that there's a right angle down to this baseline. So we probably want to extend that line. And usually when you extend it outside of the shape, you make it dashed. So now we have imaginary guidelines going around all outside of the shape. But you know what? This 8 is still the height of the parallelogram. That's really, really important because it's just one of those things that students don't see. students take things way too literally visually on paper. If they see a height here, they think, oh, that's outside of the shape. It couldn't possibly be the height of that shape because it's outside. But we understand that that really doesn't matter. It is still the height of that shape. And the base is still 20, by the way. So now, even though I have imaginary guidelines going on, for example, I might put a 10 here. Let's say like this part of the dashed imaginary guideline is 10. Many students would think, oh, now the base is 20 plus 10, which is 30. No, that's totally wrong. The base cannot include any imaginary guidelines. It must be solid side of the shape. One side, the whole side, and nothing but the side. So don't let those little visual things throw you off. So everything that we've done in this parallelogram has not changed the parallelogram. Its height is still 8. Its base is still 20. Okay, question number 8. What is the area of this parallelogram? Well, the area of the parallelogram is base times height, and we've just established that the base is 20 and the height is 8. Therefore, the area is 8 times 20. 160. Okay, now that leads us into triangles. What is the area of any triangle formed from 3 points of the parallelogram? If you take any 3 of these points, K, L, M, or N, and make a triangle out of it, the area will be half of the 160. So it will always be 80. Now I want to take a look at that for the weirdest case, which is an obtuse triangle. So question number 10 says to draw a triangle KMN, which is half of the parallelogram above, and label its base and its height. So I've drawn a diagonal through the parallelogram here, which will give us triangle KMN. And to help see this, I'm going to get rid of the actual parallelogram so that now we just have the triangle. And we just established that the area of that triangle has to be 80 because that's 1/2 of the base times height. The base is 20 and the height is 8. By the way, the 12 just doesn't matter. So the 20 now really refers to this side of the triangle. And again, the 8 represents the height, which has to be situated outside of the triangle. But there it is. And as we discussed before, that 8 is still the height of the triangle, even though it's, quote, outside the triangle. Don't let that fool you. So a lot of people have trouble with these obtuse triangles because of this issue. Hopefully drawing this out has helped see, it'll help you understand the area of an obtuse triangle next time you see one. All right, the final topic here is compound areas. And that would mean areas of weird shapes like this. There's a very simple secret for these. The good news is that there are very few area formulas you actually need to know. That really the only area formulas you need are the ones we've discussed: rectangles, parallelograms, triangles, and circles, which we covered on a different day. And then we just have to understand this principle. Areas add and subtract. No matter how strange the shape is, almost all compound shapes can be calculated by adding or subtracting areas of the 3 basic shapes. So what would be your strategy for calculating these shaded areas? I'm not going to put numbers on this, but we're going to talk about visualizing it. This is a very bizarre pentagon, but I hope you can recognize that if you make a cut across this part, you're going to break it down into a rectangle and a right triangle. And then you just simply have to add those 2 areas together. Question number 12. Here's the shaded part. Well, areas subtract as well as adding. So in order to calculate the shaded part, we would basically take the area of the large triangle minus the area of the small triangle. And finally, question number 13. So this one would basically be seen as the area of the square minus the circle, and then you'd have to divide that by 4 in order to get one of these corners.